Class, this is about buffers. That's 17.2. So let's take a quick look at this. This says solutions of a weak conjugate acid-base pair. What does that even mean? So I can say the words, but unless you know what it's talking about, then it's not very helpful. So you're going to see an example that has to do with, come on, there we go, with HF. And if I add sodium fluoride to that, you will notice that fluorine, or the fluoride ion, then is common in both of those. This is a weak acid. There's its conjugate base. So there's our acid conjugate base pair. So that would constitute like the, beginnings of a buffer. What do we know about buffers? Well, they are particularly resistant to pH changes, even when adding strong acids or strong bases. And I'm sure you're wondering, how is that possible if you're adding a strong acid or strong base? Well, here, take a look at this example. So here I have situation. This is difficult to see on the screen, the smaller things, but it says, excuse me, the addition after, the buffer after you add OH, which means adding a base. So if you add OH, then what happens is that the acid reacts with the base, which is good. It reacts with the OH ions and gets rid of that. And what's left over then is F minus and water. And neither one of these will change the pH significantly. So it's resistant to base because the HF would react with the OH, and then that just gives us this and water, which is good. Take a look what happens when we add the acid. So what if we add acid to it? Well, if acid's added, then the F minus reacts to form HF. Now, it looks like we're increasing the concentration of an acid, but HF only ionizes 1.7% of the time, which means we're only adding a very small amount of actual H+, which means the pH doesn't change very much. Okay, now if we were increasing the concentration of, say, like HCl, that reacts to give us this 100% of the time, that would make a huge difference. But because we're increasing HF, and HF is a weak acid, then it doesn't hurt the solution, or it doesn't change the pH very much. So let's keep going here. I'm not going to do these calculations. This is what's happening. You can see the Ka is written for us here. I did a little bit of this for the common ion. So let's keep going. We know all about that. Taking the negative log of both sides, we get negative log of the Ka is called the pKa. That's something we already know. The negative log of the hydronium ion concentration would be what the pH is. So here already I have pKa equals pH, and then it looks like it's going to be plus, and then I think now we can keep that the same if, and I think this ends up being a negative. Here, we have it written for us, the next. There we go. It ends up being a negative, and that's the base in the acid, base over the acid. But this is not nearly as helpful as solving for the pH. So if we solve for the pH, then all this does is change from a minus to a plus. This right here is the Henderson-Hasselbalch equation. Please write this down. We're going to be using this. Where do you find the pKa's? Well, what we can do is we can find the Ka in the back of the book, and then just simply take the pKa, let me erase that and say it like this. pKa equals the negative log of whatever the Ka is. And we have Ka's in, I think it's appendices B or D in the back of the book. So we will find common weak acid Ka's in the back of the book, and then you just do the negative log to find the pKa. That's the easiest way to do that. I'm not going to we'll go over this in sample problems, so I'm going to skip over this. I think I'm just about finished because the pH, well, here's some things we can talk about. The pH range is the range of pH values over which a buffer system works effectively. So it will resist pH up until a point, and then when you add too much acid or add too much base, then the pH will be affected. But there is like what's called the buffer capacity, and that's the amount of acid and base you can add without changing too much. So think of it like this. Think of our range like this. Here's our pKa. Okay, if I add too much, this would be pH of 0 and of 14. And if I got a pKa like close to 7, like this, that means you could add a decent amount without changing the pH significantly if you have a big buffer capacity. Okay, so you want to, if you're looking for a buffer to be around pH of around 4, then you would want a pKa of an acid to be around 4. Okay, that's what you're looking for. So when strong acids, strong bases are added to a buffer, so this is the kind of steps for figuring out. So I'm not going to go over this very long. Our first step, though, is by reacting the acid and the base. When you react the acid and the base, and then this is what we do the equilibrium part on here. So our first step is to figure out how the acid and base interact. Once we figure that out, then what's left over will be a strong acid or a weak acid or a weak base, and that's when the equilibrium calculations come in the form of ice. So we're going to figure out the amounts first by acid-base reactions, and then that will take us to the ice reaction. That's how buffers work. Additions of a strong acid or strong base to a buffer. Here's another example. This one, though, is with acetic acid and sodium acetate. And when we add, notice this, that when I add a little bit of acid, the pH goes from 4.74, which is also the pKa for this one, which drops down to 4.68 by adding a little bit of concentrated acid. That's all the drop there is. That's almost nothing. That means almost nothing there. And if I add a strong base, it goes from 4.74 up to 4.80, which again is like almost nothing. So we will figure out, I'm not going to show you how to do this here. Like I keep saying, I'm holding off. So the pH that we start with is also the pKa. You can find that by taking 1.8 times 10 to the negative fifth. That gives us the pKa to start, and then we can find the change overall. This is the stoichiometry part that it was talking about. We find how the acid interacts with the base first. So if I'm adding 0.02 moles of, where are we at here? NaOH, like that. That means if I start with 0.3 moles here, I subtract the amount of the base, and that will give me the new amount, always missing zeros, of the number of moles of the HAC, which is the acetic acid, which is what we got right here. This is the stoichiometric part, and then we get into our ice, or we can just go right into the Henderson-Hasselbalch equation, which is what this is right here. And we don't have to do our ice equation. Okay? Thanks for paying attention, guys. I'll explain more thoroughly for the sample problems.